Our next topic in the physics of sound is the cyclical nature of sound waves and some of the measures that we use for them. So most of the sounds that we'll look at have repetitive pressure changes that we can describe in terms of cycles of vibration. So thinking of our basic waveform, for example, we have an increase in pressure for compression, a decrease in that pressure back to atmospheric pressure, a decrease in that pressure below atmospheric pressure for rarefaction, and a return to the baseline atmospheric pressure. That would define one cycle of a sound. We can measure the rate of that vibration in terms of cycles per second. That is usually referred to as a frequency and measured with the unit of hertz, which is the same as cycles per second. After an acoustician from back in the day. For one of these repetitive sounds, the period, in terms of the duration of time, is the time it takes for one cycle of vibration to occur. If we have a period of 4 milliseconds, for example, 0.004 seconds, the number of cycles in 1 second can be computed by taking that one cycle, dividing it by the period of 0.004 to get us 250 cycles per second, or a frequency of 250 hertz. So our formula for frequency is 1 divided by the period. If we have the period for one cycle, you can equivalently measure the frequency by looking at several cycles, in which case the computation would be the number of cycles, how many it is, 2, 3, 4, 5, 10, whatever, divided by the duration of that number of cycles. So if you have 4 cycles, the duration of those 4 cycles would be what you would use in the computation. Given math, we can also do things the other way. So the period is 1 divided by the frequency. For example, if I have a frequency of 400 hertz for a sound, 1 divided by 400 gives us 0.0025 seconds, or 2.5 milliseconds, as the period. This cycle from compression to rarefaction and back to compression has been described as being quote-unquote simple harmonic motion. This happens when you have a restoring force on an object, like elasticity, is proportional to the displacement of the object from its equilibrium position, but in the opposite direction. So basically, something that's vibrating fits this definition of simple harmonic motion. You can get a sound based on simple harmonic motion out of something like a tuning fork, given the long tines that fork has on it. If you hit it against something so that it vibrates, that vibration will affect the air molecules around it, creating sound waves and cycles of compression and rarefaction. The resulting waveform graph that we get, that's on the bottom right in this image, is sometimes also called a sine wave because the mathematics of the trigonometric sine function gives you that shape, and we can use that mathematics to synthesize sounds. That's what we've been doing in our lab examples with the prop program. This kind of wave with one cycle of compression and rarefaction is also referred to as a simple periodic wave or as a pure tone. Some definitions related to this concept. A sound is periodic when it has cycles where each of the cycles take the same amount of time to occur. Perceptually, when a sound is periodic, it will have a degree of musical tone to it. It will have a specified pitch to it that we can hear. If a sound is not periodic, then it is aperiodic. An aperiodic sound would be a wave where we have cycles that don't take the same amount of time to occur. So these sounds have no specific frequency or period. They are visually irregular when we look at them on our graphs. We get this kind of sound out of things like noises or clapping our hands or hissing sounds. In addition to their period and frequency, periodic sounds have a wavelength. I mentioned earlier that we can talk about sound waves as they change over time hitting a microphone, or we can talk about them as they propagate over distance in a room, for example. Wavelength is that axis for propagation over distance. The symbol that gets used for wavelength is the Greek lambda, and the wavelength is the distance traveled by a sound wave in a single cycle. We'll compute wavelengths in terms of centimeters because that's a good scale for the vocal tract. These measures we have of a basic sound wave in terms of frequency, period, and wavelength are all related to each other. As the frequency of sound goes up, or if a sound is higher in frequency, its period is going to be a shorter duration of time, and its wavelength is going to be a shorter distance. A sound that is lower in frequency has a period that is longer in time or longer in terms of a distance covered by one wave in space. We can do math with wavelength. Since it depends on sound propagating over a space, the speed of sound is involved. So the frequency of sound is equal to the speed of sound divided by the sound's wavelength. For example, if we have a sound with a wavelength of 12 centimeters, that would actually be a sound that would fit reasonably well inside a human vocal tract, for example. We would compute the wavelength as 34,400, our speed of sound in centimeters per second, divided by those 12 seconds to get us 2,867 hertz. Again, math allows us to move things around. The wavelength of a sound is equal to the speed of sound divided by its frequency. So for example, if we had a sound with a frequency of 800 hertz, its wavelength would be the speed of sound, 34,400, divided by that 800 hertz to give us a wavelength of 43 centimeters. Since the period, frequency, and wavelength are all related to one another mathematically, one of them is sufficient to describe the periodicity of a sound. Usually frequency is the value that's used to describe that periodic sound, in part because when we hear periodic sounds, frequency is what the ear responds to.